everyone, and thanks for watching Edupedia World Videos. This is the second video on the topic heat transfer. In the previous video, we talked about conduction and a little bit about convection. This video is about radiation. Radiation is the third form of heat transfer, and it is defined as transfer of heat without a medium. Actually, it's transfer of energy without a medium, but right now we are talking in the context of heat. The most common example of this would be the fact that we receive heat from the sun. There is nothing in between the earth and the sun, it's just empty space, yet somehow heat and energy are able to be transferred from the sun to the earth. That mechanism is radiation. Right. Now, whenever radiation falls on a material, one of three things happen. Okay, first of all, you need to know this. All electromagnetic radiation has particular wavelengths. It is in the form of waves. And when the wavelength, let's say this is the complete spectrum of electromagnetic wavelengths. So you can have gamma rays here, you can have X-rays here. There is a very small tiny portion which is called visible light. So human beings cannot see most electromagnetic radiations. We can only see that particular electromagnetic radiation which lies between a particular specific value of wavelengths. And one of them is red and one of them is blue. Those are the two extremes. But from a scientific point of view, it is all electromagnetic wavelengths. The particular wavelength doesn't matter. It's all electromagnetic radiation. So, whenever electromagnetic radiation falls on a surface, a few things can happen. The radiation can be reflected, or it can be transmitted. Transmitted is just another word for refracted, or it can be absorbed. Right. So just think of radiation as a form of energy. So energy can arrive at this place and then it can go back. That means it cannot affect this particular surface at all. It can be transmitted through this surface, or it can be absorbed by the surface. In this case, the energy of the surface will get increased. Of course, the total fraction of energy reflected plus fraction of energy transmitted plus fraction of energy absorbed will have to add up to 1, because the total energy falling on any surface will have to either be reflected, transmitted, or absorbed. Right. There is a very special kind of body which we talk about in radiation, and that is called a black body. The definition of a black body is that it absorbs 100% of the radiation falling on it. Right, so any energy or any light, when it falls on the black body, none of it is reflected, none of it is transmitted, all of it is absorbed by the black body. Right. This is sort of like the ideal body in radiation, and we measure all performances of other bodies in comparison to black bodies. Right. Now, and a particular thing which confuses students is, and it's natural because black body is sort of not really named accurately, a black body is not necessarily black. Of course, it does not reflect any energy, but it can radiate its own energy. Right. So every object in the universe radiates some energy. There has never been an object which does not radiate any energy. Every object radiates a certain amount of energy. Right. Now what happens is, if the amount of energy radiated by an object is greater than the amount of energy absorbed. So let's say this is an object and that this is kept in a room. So in equilibrium, the room will be absorbing some energy, the room will be radiating some energy, this object will be absorbing some energy, this object will be radiating some energy. And if none of them are black bodies, there will obviously be reflection and transmission as well. For a second, we'll just assume that reflection and transmission does not occur. We'll just talk about radiative energy and absorbed energy. So let's look at this particular body. It is obviously radiating some energy, as every body does. and it is obviously absorbing some energy which is being put onto it by the surroundings, because the walls of this room will also radiate some energy on its own, just like every body does. Some of that energy will be absorbed by this object. So for any object, if the amount of energy radiated is greater than the amount of energy absorbed, then the temperature of the object decreases. It seems natural, right? If an object is radiating a lot of energy but not absorbing any energy, in the end its temperature will keep on decreasing, because temperature measures heat and heat is another form of energy, right? If the energy radiated is less than the energy absorbed, that means it is absorbing more energy from its surroundings than it is radiating, then the temperature increases. And if the radiated energy is equal to the absorbed energy, then the temperature is constant. So any object on equilibrium, you look at your table right now, I have a keyboard. The temperature of that keyboard is not changing with time. That obviously means that it's radiating as much energy as it's absorbing. It is not radiating zero. Every object radiates some amount of energy, right? So it is radiating some energy and it is absorbing some energy from its surroundings, maybe the monitor or the keyboard or the walls. And for the keyboard, monitor or the printer or the wall, sorry. And for the keyboard, the total amount of energy radiated is exactly equal to the total amount of energy absorbed, because its temperature is constant with time, right? Now let's look at the black body again. We say that the black body absorbs 100% of the radiation falling on it. Okay, let's assume the black body was completely black. That means not only is it not reflecting any energy, it is not radiating any energy. An object not radiating any energy but absorbing all of the energy falling on it, its temperature is going to rise fast, right? But that does not happen. For a black body at equilibrium, if it absorbs all of the energy falling on it, then it must also radiate an equally large amount of energy. And this is where students get confused, because they think a black body means it does not radiate any energy. No, a black body means it does not reflect any energy falling on it. It absorbs all of it, but if it is absorbing energy and it is in equilibrium, it has to radiate energy. In fact, not only does the black body radiate energy, black body radiates the most amount of energy, because it absorbs the most amount of energy. If there are two objects in a room, one of them is a black body, the other is not, both of them are in equilibrium, the black body will be absorbing more energy. Hence, it must be radiating more energy, right? This body will be absorbing less energy and radiating less energy. The total of both of them will be zero, absorption minus radiation, because they both are in thermal equilibrium. But the amount of energy absorbed and radiated will be different for all objects. So that is why black bodies are also called ideal radiators, right? So this is an important, which at first, even when I learned it at first, it gave me a little bit of confusion. So I'll repeat it again. Every body in the universe at every point of time radiates some energy, okay? And if the temperature of an object is constant, then it must also be absorbing some energy. You cannot just radiate energy and keep the temperature constant. Conservation of energy has to be valid. So every body radiates energy, every body absorbs energy. If it radiates more than it absorbs, temperature decreases. If it radiates less than it absorbs, temperature increases. A black body absorbs most radiation among all bodies, and it is in equilibrium. If it is in equilibrium, obviously, then it must radiate the most amount of energy as well. So we seem to have reached a sort of contradiction in terminology. A black body is not a body which doesn't radiate any energy. It's not a body which looks black. In other words, if you consider visible light, it will radiate energy. It just does not reflect any energy. Any light you shine on it will just be absorbed by the body, right? So let's look at a few quantitative terms that are used when measuring radiation. One of them is emissive power, and it is a measure of how much a body radiates energy. It is defined as delta U by delta A, delta W, delta T. Delta U is the energy radiated, so it will be in joules. Delta T is the time, so energy radiated per unit time, energy radiated per unit area. So if we have a surface and it is radiating some energy, of course, the more area there is, the more energy will be radiated from the surface. So emissive power is a measure of the surface energy radiated per unit area as well. And this last thing, I'm not sure if you're familiar with it or not, is called a solid angle. Now actually you should be familiar with it. I covered this in the very second or third video on units and dimensions. But I'll just give a little bit of recap in case you didn't. Just like plane angles can be measured by taking this point as a center and constructing an arc and calculating the length of this arc, dividing it by the radius, that will give me the angle, and we find out that the length by the radius will be independent of the radius. If you take a bigger arc with a bigger radius, the length will be proportionally large. So the ratio is called the angle. Similarly, if you imagine a cone, instead of just two-dimensional, it's three-dimensional. If you imagine a cone, then if you keep your center at this origin and you create a part of a sphere, now it's not an arc, now it's a sphere, right? So this will be a sphere. You calculate this area, you divide it by r squared, right? You'll be able to see that it is independent of the radius. If you construct a bigger sphere, part of the sphere, the area will be proportionally greater to r square. If r squared is doubled, the area will be doubled. And so just like angle is measured as L by R, omega solid angle is measured as A by R square. The total area is 4 pi r square, so the total solid angle in space is 4 pi, just like the total circumference is 2 pi r, so the total plane angle is 2 pi. Right? So omega is always between 0 and 4 pi, and it just depends on how much of a cone you are looking at. If you have a point object and you want to look at just this particular region, then you'll just take this solid angle instead of all of space. Right? So this is emissive power. It is a measure of the energy radiated per unit area, per unit time, per unit solid angle. Right? The second important quantity is absorptive power. Now emissive power was not a dimensionless quantity, but absorptive power is. It is simply the energy absorbed by the energy incident. So for example, if 10 joules of energy are falling on a body per unit time, per unit area, per unit solid angle, right? So if 10 joule of energy is falling on an object and it absorbs only 5 joule, and it either reflects or transmits 5 joule, that is, out of 10 joule 5 joule will be absorbed, the rest of the 5 joules can be distributed between reflection and transmission in whatever manner. So in that case the absorptive power would be half. The absorptive power is equal to 1 for, that's right, you guessed it, black bodies. That is sort of the definition of a black body. It will absorb 100% of the energy incident on it. So the absorptive power is greatest for black bodies, and for any other object which is not a black body, it lies between 0 and 1. Sorry, it shouldn't be alpha, this is A. It is denoted by A. So for any other object, absorptive power lies between 0 and 1. Similarly, there is emissive power. Emissive power is, sorry, we already did emissive power. Emissivity. There is emissivity, which, just like absorptive power, is a dimensionless quantity, and it is the energy radiated by a black body at same temperature. So if a we know that the black body, because it absorbs the most energy, it radiates the most energy as well, right? So if a black body at a certain temperature radiates 10 joules and another body at the same temperature radiates 4 joules, then it has an emissivity of 4, right? Obviously again emissivity is equal to 1 for black bodies. So now you see the use of black bodies. They are sort of the ideal material for us, and everything else is measured in comparison to them, right? When an object is in equilibrium, it is absorbing as much as it is radiating. So in that case, A is equal to E. And both of them lie between 0 and 1 for bodies which are not black bodies. Okay. Now comes an important law when it comes to studying radiation. It is called Kirchhoff's law of radiation. It basically says that at a given temperature, E of any body, remember capital E is emissive power, small e is emissivity, by A of that body is equal to E of a black body, right? You could write divided by A of a black body, but that is always 1, right? So this is Kirchhoff's law. Now it might seem redundant to you because we've already studied this. A of a body was E body divided by the black body, but it's sort of a matter of chronology. Kirchhoff's law came first before the other definitions came, and radiation was studied in detail. So historically it is an important law which you need to know about. What it basically says is that every body has A smaller than A of a black body. That means every body has E smaller than that of a black body, right? These are radiated energies, by the way. So Kirchhoff's law was basically another way of saying that bodies which are black bodies radiate the most amount of heat, right? Bodies which absorb less heat radiate less heat, and bodies which absorb more heat radiate more heat. But that was where we started from, right? Because if everybody is in equilibrium, then everybody is absorbing as much as it's radiating. So the people who are radiating large will absorb large, the people who are radiating small will absorb small. Now let's deviate a little bit. The next important thing to study is how that energy is distributed among different wavelengths. Wavelengths can range from a wide variety. It can range from 10 to the power minus 15 meters to the order of 100 meters, from gamma rays to radio waves. A very small spectrum in between is what we call visible light, and that is what we can see, right? But if any object is radiating energy, just like every object radiates energy, every object technically radiates energy at all wavelengths. That means if this is an object radiating some energy, or my keyboard is radiating some energy, it will radiate at least some energy in the form of gamma rays. It will radiate at least some energy in the form of radio waves. It will radiate at least some energy in the form of visible light. It will radiate some energy in the form of waves, right? And we measure the distribution of energy with wavelength by measuring what is called the intensity. Intensity is simply the energy radiated per unit time per unit area, right? And we can measure the intensity versus wavelength graph, and for all objects the structure of it is like this. Like I said, every object radiates light at every wavelength, so we'll draw a graph of that, right? So the graphs are always something like this. Sorry, right? So every object radiates a very small energy at extremely small wavelengths, very small energy at extremely large wavelengths, and there is a particular maximum radiation wavelength, a wavelength at which maximum amount of radiation is given, right? So this is the energy versus lambda curve for any graph, and we can measure this particular lambda, which is called maximum intensity lambda, or lambda max. A scientist called Wien actually gave a law which tells us how this lambda changes with temperature, right? So the law is lambda max times d is equal to 0.288 centimeter Kelvin, which is called Wien's constant, and this whole thing is called Wiens displacement law. Apologies for the writing. Displacement law. right? So it tells us that as the temperature increases, lambda maximum decreases, and as lambda decreases, we go higher and higher into the X-rays and gamma rays. So this sort of tells us uh, why certain objects look a certain way. When we heat something, the color changes because the temperature changes. As the temperature changes, the maximum intensity given out at a particular lambda changes. So for example, if an object is initially giving out energy, its temperature will change. And for example, initially if it was giving um, a maximum energy at a wavelength of uh, 10 nanometers, and we increase the temperature, it will now give energy at a wavelength of 8 nanometers. That means its color might change. Its color will change if that particular lambda max lies in the visible region. Right. There are two more small topics left. One of them is an important law. It's called the Stephen-Boltzmann law. And I'm just going to give it to you right now. But uh, when I entered second year in college, we studied a course called Statistical Mechanics, and in that we can actually learn how to derive this law from the basic principles. Right now you're just going to have to remember it. The law is U is equal to sigma A T to the power 4. U is the energy radiated, A is the surface area, T is the temperature, and sigma is the Stephen-Boltzmann constant, and it has a value of 5.6 into 10 to the power minus 8 SI units. I don't remember what those are, you can calculate them. This is the value of sigma. This is valid for black bodies, right? For black bodies, now we know if I give you a black body of a certain surface area or a spherical black body of a certain radius, and I give you the temperature, you can directly calculate the total amount of energy radiated, right? Now we know that for other bodies, the energy radiated is reduced by a factor of E. So this is the equation for any body where E can lie between 0 and 1. If E is equal to 1, we are talking about the black body, and U is equal to sigma AT to the power 4. If E is between 0 and 1, say half, then that body does not radiate as much energy as a black body. Right. So the final thing is something which is natural to do once we've learned the energy absorbed and the energy radiated. It is to relate it with the change in temperature. Right. So let's say we have an object, and we have it in a room, right? The object is radiating some energy, the object is absorbing some energy from the room is radiating some energy, the room is absorbing some energy from the object, right? Let's say the temperature of the room is T surrounding and the temperature of the object is T. The energy radiated by the object will be E sigma A T to the power 4. Right, let's assume its area is T. This is the energy radiated. How do we calculate the energy absorbed by this object? I can use a tricky argument to calculate the energy absorbed by this object. So if the temperature of this object was Ts, then it would be radiating an amount of energy equal to sigma E sigma A Ts to the power 4, right? If it was at Ts, this is what it would be radiating. If it was at Ts, it would be at equilibrium, because this is also at Ts. That means if it was at Ts, this is the amount of energy it would be absorbing, right? Now the second argument is the amount of energy absorbed by this object does not depend on its temperature. It depends on the temperature of the surrounding, and it depends on the geometry of the object, right? Surface area and so on. So as the temperature of this object will have no effect on the energy absorbed by this object. So regardless of what the temperature is of this object, the energy absorbed by it will be sigma ATS to the power 4. This is a tricky argument, I'll repeat it again. We know it's radiating sigma AT to the power 4. If this was Ts, then it would be radiating E sigma ATS to the power 4, and it would be absorbing the same amount. So we know that at Ts, this is what it absorbs. And then we use the argument that the energy absorbed by this object will not depend on its own temperature at all. So this is the energy absorbed always, right? So what is the change in energy of the object? It will be E sigma A T to the power 4 minus Ts to the power 4. Right. This is the rate of change of energy. Now we can write it as E sigma A T to the power 4 1 minus Ts by T whole to the power 4. Right. This is delta U. Now Newton actually used this result, and he used an approximation to get a much easier result, which could be solved much more quickly. So that result was, we've gone to delta U is equal to E sigma A T to the power 4 minus Ts to the power 4. He said that he is going to solve for the cases in which T is approximately equal to Ts. Right. This solves a very small subset of the cases, but if, for example, you wanted to measure out the change in temperature of a cup of water, then you could use this if the temperature was not much higher than the temperature of the surroundings. Right. So he wrote T is equal to Ts plus dt. Right. So from that we got this, and this will also be du because the difference will also be small. So du is equal to E sigma A Ts plus dt whole to the power 4. So all other terms will cancel except Ts to the power 4 plus 4 Ts cube dt. Right. And that will cancel with this. So what will remain is 4 Ts cube dt. That gives me du by dt is equal to E 4E sigma A Ts cube. We'll just take dt, I don't know why I took it down. We'll just take it to this side and we'll write it again as T as T minus Ts. Right. So the result we get is the small change in energy is proportional to the difference between the temperature of the object and temperature of the surroundings. So the short thing which he derived was du is equal to B1 times T minus Ts. Right, a particular constant. This is for radiation, and by calculating convection he was also able to find out that this is equal to B2 T minus Ts for convection. You don't need to know how that is done. This is radiation, this is convection. So the ultimate result which we found out was du, which is proportional to the change in temperature per unit time, is equal to, this is delta U actually, the change in temperature per unit time, it is equal to minus alpha, alpha is just beta 1 plus beta 2, times T minus Ts. This is Newton's laws of cooling. He involved a lot of approximations to do this, and that's why you sort of cannot use it in all problems, and it does seem to lead to many errors even if T minus Ts is slightly large. But when T is approximately equal to Ts, what this law tells us is that the rate of change of temperature is proportional to the difference between the temperature of the object and temperature of the surrounding. This is called Newton's laws of cooling. So if there is a temperature of a room 20 degrees centigrade, and there's one object which is at 50 degrees centigrade, and there's another object which is at 80 degrees centigrade, and there's another object which is at 110 degrees centigrade. The difference between the temperature of the object and the temperature of the surroundings is 30, 60 and 90. So this object will decrease its temperature 3 times as fast as this object. This object will decrease its temperature twice as fast as this object. Right. So that's what Newton's laws of cooling tells us, is that the rate of change of temperature is pretty much proportional to the difference between the temperature of the object and the temperature of the surrounding. Now again, this is not exactly valid because 50 minus 20 is 30, which is not a small number, but this is technically only valid for T minus Ts to be quite small. This completes heat transfer. Thank you.